Okay, so this is probably not the best way to teach this lesson, but we just got to make do with what we've got. So let's read here. It says degree measures. A second way to measure angles is in terms of degrees. So this is what you're more familiar with using. You know, we spent all day yesterday working on radians and how we could break radians up as fractions. All right, well, those radian measures have an equivalent degree measure that goes with them. In pre-cal, if you don't see a degree sign, then you know it's in radians. But if you see the degree sign, we're talking about it in terms of degrees. So anytime we're talking about degrees, you're going to see the degree symbol. So the measure of 1 degree is equivalent to a rotation of 1 out of 360 of a complete revolution about the vertex. So all that's saying is 1 degree, you need 360 of those to make a full revolution, which we already know that. To measure angles, it is convenient to mark degrees on the circumference of a circle, as shown in figure 4.7. So a full revolution, and again, we're going counterclockwise, will be the positive rotation, corresponds to 360 degrees. If I go halfway around the circle, that's 180 degrees. A quarter revolution, that means a fourth of the way, would be 90 degrees, and so on. 1 complete revolution corresponds to 2 pi radians. So degrees and radians are related by the equations. 360 degrees is equal to 2 pi radians. And if I divide both sides by 2, that tells me 180 degrees is pi radians. So this is going to be our conversion. We're going to use this formula on all of our problems here in the future, where it asks me to convert from degrees to radians and radians to degrees. You should have seen some of this in your geometry class, so it's not going to be brand new to you to convert. All right, but let's look here really quickly on some of their rotations. So you can see here, our big rotations are going to be 30 degrees, 45 degrees, 60 degrees, because we're going to be working towards special right triangles, as I mentioned yesterday. So as you can see, right here, this is my pi over 2. Radian measure is 90 degrees. Well, if I half that, this would be pi over 4, which is at 45 degrees. So 45 degrees and pi over 4 are the same thing. 90 degrees and pi over 2 are the same thing, and so on. All of these rotations are just 30, 45, and 60 away from the previous rotation. Right? So if I was 90, I could go another 30, I could go another 45, or I could go another 60. To get from 180 to these rotations, I could go another 30, I could go another 45, or I could go another 60. Another way to think about that, this would be pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3, or 2 pi. Right? So every one of these tick marks is increasing by 1/6. Right? Maybe I did that backwards. So this should have been, let me do it again. This would be, if this is pi, then this would be another third of the way. I'm sorry, another 1/6 of the way. So this would be 7 pi over 6, 8 pi over 6, which is 4 pi over 3. This would be 9 pi over 6, which is 3 pi over 2. This one would be 10 pi over 6, which is 5 pi over 3. This would be 11 pi over 6. And then 12 pi over 6, which is 2 pi. So you can see I can hit all these tick marks by rotating pi over 6. All right, and then to find the one between them, that's when we rotate by pi over 4. So this is 1/4 pi, or pi over 4, pi over 2, 3 pi over 2. I'm sorry, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4. So the 45, 90, 135, 180, those are all from rotating 45 degrees around, or pi over 4 radians. Okay, so these problems here we're going to be converting from degree measures to radian measures. So like I said, if you don't understand that whole explanation I gave about radians to degrees and on the unit circle, that's okay. We're going to be spending more time with that in section 2. All you really need to know for this section is how to convert from degrees to radians and from radians to degrees. So we know our conversion rate is pi radians is equal to 180 degrees. And so if you want to think about it, the way we could do this, if we solved it, we could divide both sides by 180, and then that would cancel and say 1 equals pi over 180. That's an option. Or we could have pi equals 180, and we could divide both sides by pi. And if we do that, that's going to tell me 1 equals 180 over pi. So these two are conversion rates. It really just depends on which one needs to go in the numerator. Do I need radians in the numerator, or do I need degrees in the numerator? So I used to always get mixed up, and I would do it backwards, and I'd put the wrong one, because I know that you like to remember little tricks, like, well, to get there, I just divide by 180 and then multiply by pi. Or I could multiply by 180 and then divide by pi. Well, how do you know which one is which? This is the way I always set it up. So if it starts in degrees, 135 degrees, I know I want to get rid of my degrees. So in order to get rid of degrees, I need the degrees to go in the denominator. So I'm going to take this conversion rate here. I'm going to put the degrees in the denominator, which means the radians goes in the numerator. This ensures that my degrees cancel, numerator and denominator. And so now I've got 135. I can put that over 1. So 135 times pi over 180. That's going to be 3 pi over 4. So again, you can put that in your calculator and get that. The next one here was 540 degrees. If I'm converting that to radians, again, I want degrees in the denominator. So I'm going to put 180 in the denominator, pi in the numerator. And so again, these degrees are going to cancel. That's why I do it that way. And then 540 divided by 180, that's going to be 3 pi. So 540 degree rotation, that means we're basically rotating. This would be 1 pi, 2 pi, 3 pi. Right? Because I rotated 360, and then I rotated another 180, which is 540, which is in radians 3 pi. Okay, so now they want you to convert both of these from degrees to radians. So pause the video, try it on your own, and then you can check your answers with me. Okay, if I had 75 degrees, I'm going to put degrees in the denominator. So that's 180 in the denominator, pi in the numerator. Pi's cancel. That leaves me with 75 pi over 180, which will reduce. And again, you can put that in your calculator. I don't have my calculator, so I'm going to have to reduce twice. That's going to be 15 pi over 36, and that will reduce again. That is going to be 5 pi over 12. So A part, you should have gotten 5 pi over 12. And then for B part, same thing, pause the video and try it. If I've got 320, I need to put degrees in the denominator to make those degrees cancel. So that's going to be 32 pi over 18, which would be 16 pi over 9, and that does not simplify. So 16 pi over 9 should be your answer for B part. So now these questions, we are starting with radians, and we're wanting to convert to degrees. So this is basically the opposite of what we were just doing before. I still have that same conversion. 180 degrees is still equal to pi radians, but now I need radians to cancel. So if radians is in the numerator over here, the way I can get rid of that is to get radians in the denominator. So if we think about dividing both sides by pi radians, that means my conversion is going to be 180 over pi this time. So when I set it up for A part, I've got negative pi over 2, and this is in radians. That's going to be multiplied by 180 degrees over pi. Okay, so this time, my degrees don't cancel. That's good. That means I'm going to have degrees left in my answer. So in this case, the pi's cancel, top and bottom, and I have negative 180 degrees over 2, which is negative 90 degrees. So again, this is going to be a rotation clockwise to go down to negative 90. That's what the negative tells me. The negative tells me the direction of the rotation. So again, I would be going clockwise, which means I would be going in this direction. And then B part, this one's kind of an odd one because there is no pi. So people get confused. They think I didn't see a pi, so that means this must be in degrees. That's not true. This is 2 radians. So because it's in radians, I need my radians to go in the denominator so that they cancel, which means 180 degrees goes in the numerator. So I could cancel the radians. So now my answer here is going to be 2 times 180, which is 360 over pi. And then this would be my exact answer. It may ask you to round. So if I put that in my calculator, 360 degrees over pi is going to be approximately 114.59 degrees. Okay, so here on this problem, we have 2 angles that are in radians, and it tells me to convert them from radians to degrees. So if you'll pause the video right now and try it on your own, and then I'll show you how to work them. Okay, so if I start here with pi over 6, again, that's in radians, and I want to convert it to degrees. So I need to put my radian measure in the denominator. So again, that's going to be pi radians. That way the radians will cancel out. And then I'm going to have degrees in the numerator. So I've got 180 degrees over pi radians. So again, the radians cancel and cancel. This time pi is going to cancel. That leaves me with 180 over 6, which is going to be 30 degrees. So pi over 6 is 30 degrees. And again, that's one that you're going to see a lot of, so I actually have that one memorized. All right, on B part, same idea. I have 5 pi over 3 that's in radians. So I want to multiply that by 180 degrees over pi radians. Again, I put radians in the denominator, so that way they cancel out here. Also have a pi in the numerator and denominator. Those will cancel. And then 180 over 3, that reduces to 60 over 1. So 5 times 60 is 300 over 1, which means 5 pi over 3 is 300 degrees. Okay, the next thing we're going to talk about here, this is kind of a review of angles. And we're going to be talking about a couple vocabulary words, which are complementary angles and supplementary angles. It says 2 angles are said to be complementary if their sum is 90 degrees. So 2 angles that form a right angle together, those 2 angles are complementary. If I have 2 angles that form 180 degrees together, or a straight line, those are said to be supplementary. So when you look here in the first example, beta and alpha, those would be complementary angles because together they form a 90-degree angle. And then in this one, beta and alpha, they form a straight line together. So that means together they are 180 degrees, or they are supplementary angles. So right here it gives me 4 angles. It wants me to find both the complement and the supplement for each one of them. So let's start with A. A is 72. To find the complement of 72, I want to know what added to 72 is 90, and that's going to be 18 degrees. So the complement of 72 would be 18. For the second part, find the supplementary angle. So 72 plus what is 180 degrees? That would be 108 degrees. 72 plus 108 would be 180. Let's look at B part. B part, it starts as 148 degrees. So in order to have a complement, that means it has to add to be 90. Well, to add to 148, I would have to have a negative angle to have something that would be complementary. In terms of complementary and supplementary, negative angles do not work. So the complement of 148 degrees does not exist because the complements have to be positive. And so because it has to be negative, that's no-go. Supplementary, that would be what adds to be 180. So 180 minus 48, that's going to be 32 degrees for B part. C part, it's in radians. So again, you could take this in radians, convert it to degrees, and then find the supplement and complement, or I'm just going to leave it in radians because we have to get comfortable working with radians. So I know in order to be complementary, it has to be 90 degrees, which is pi over 2 radians. So if I'm looking for what's going to make this pi over 2 radians, I want to think here. 2 pi over 5, that's the same thing as 4 pi over 10. Right, I multiplied the top and bottom by 2. And then, again, if I'm looking to make this be pi over 2 is the same thing as 5 pi over 10. So I guess I need to explain why I did that. I turned this into 4 pi over 10 because 2 and 5, their least common multiple is 10. Right? I couldn't write them in terms of each other until I made it become 10 in the denominator. So pi over 2, multiplied by 5 on top and bottom, that's 5 over 10. 2 pi over 5, multiplied by 2 on top and bottom, that's 4 pi over 10. So basically, I'm taking 4 pi over 10, and I want to make it become 5 pi over 10, which means I need to add another 1 pi over 10. So the complement of C would be pi over 10. And then in order to find the supplement would just be adding another 90 degrees, or adding pi over 2 to it. So for these, I'm going to take the supplement, which is here, and I'm going to add pi over 2. I'm going to add 90 degrees to it. So again, pi over 10 plus pi over 2, we'll get a common denominator. So 5 over 2 becomes 5 pi over 10. So 1 pi over 10 plus 5 pi over 10 is going to be 6 pi over 10, which reduces to 3 pi over 5. So the supplement of B would be 3 pi over 5. And then D part, all right, we're starting off with 4 pi over 5. Well, I look at that and I can tell I'm really close to 5 pi over 5, which would be 180 degrees. So there isn't going to be a complement. There isn't going to be a 90-degree angle that meets that criteria, but let's just confirm that. If I make this into a common denominator, I have 8 pi over 10, and then I'm wanting to make this pi over 2, which would be 5 pi over 10. So in order to go from 8 pi over 10 to 5 pi over 10, I'm going to have to subtract, which is going to be a negative angle, which again confirms that the complement does not exist. So there is no complement. And then to find the supplement, I want it to be equal to pi. Right, so I'm going to take 4 pi over 5. And what do I need to add to that to make it be pi, or 180 degrees? That would be pi over 5. Because 4 pi over 5 plus another pi over 5 gives me 5 pi over 5. Okay, we can try these 4. So pause the video, you try them, and then I'll show you the answers once you come back. So for A part, the complement would be 54 degrees. The supplement would be 144 degrees. For B part, the complement would be none. It does not exist. And the supplement would be 89 degrees. For C part, the complement would be pi over 3. The supplement would be 5 pi over 6. And for D part, the complement would be none. It does not exist. And the supplement would be pi over 6. So our next set of problems is really the application of this trig in real-world examples. So we're going to be basically working a lot of problems that you would see in a physics book. So it says we're looking at linear speed versus angular speed. So linear speed is what you're used to. If you're driving in a car, how fast can you go in a straight line? That is your linear speed. How fast are you driving? Angular speed would be, think about you're on one of those merry-go-rounds. You know, like they used to have at the parks, but they don't have anymore because they're dangerous, so nobody can get on them. But if you've ever been on one and somebody's spinning you around, where is it that you want to be? Like, where is the place that you're moving the slowest? That would be in the center. Because in the center of the circle, in the center of the merry-go-round, you're not traveling near as far. But the closer you get to the outside and they're spinning you around and around, your angular speed is increasing. And you're feeling like you're fixing to fall off the merry-go-round. So that's going to be kind of the two things we're looking at. So that's a way to distinguish the difference between the two, linear speed versus angular speed. So the radian measure can always be given by the formula theta equals S over R, where S is the arc length and R is the radius of the circle. So again, arc length, all arc length means is the distance along the outside. We're just going to be looking at some part of that. Sometimes our arc length could be all the way around, so it's the same thing as the circumference when we talk about that. But arc length could just be any part of a circle. This could be an arc length, or all the way around could be an arc length. Okay, so let's look at the formula for arc length. It says for a circle of radius r, a central angle theta intercepts an arc length s given by s equals r times theta, where theta is measured in radians. Note that if r is 1, then s is theta, and the radian measure theta equals the arc length. So all that's talking about is when we're dealing with a unit circle, which is what we're going to be doing a lot of next section. It's saying that if I have a radius here of r, and I have some angle theta that I've rotated around the radius, when I multiply the radius times that theta, and the theta has to be in radians, it's going to give me the distance that I've traveled here. That is my arc length, S. So the first problem here is just going to be finding the arc length. So it tells me I have a circle of radius 4. So draw it. I have a circle whose radius is 4. Find the length of the arc intercepted. So we want to know what is this length here. That's what I'm looking for. I'm looking for the S. When my theta that I am rotating is 240 degrees. So we kind of have to know 240 degrees. Again, think about it. Right here, that would be 180 degrees. That's a straight line. So 240 is a little bit farther than that. So that puts me there in the third quadrant when I rotate that. But I know that this angle here that's being rotated is 240 degrees. Now, in order to use the formula, S equals R times theta, I mentioned it before, my theta, which is the number, is the degree measure that I am rotating, the theta has to be in radians. It can never be in degrees because we can't do math with degrees. We have to convert that to radians. So I'm going to take 240 degrees and I'm going to convert that to a radian measure. So again, think about our conversions we did. I'm going to put 180 degrees in the denominator, and I'm going to put pi radians in the numerator. This is going to make the degrees cancel. And so now I have 240 pi over 180, which that reduces to be 5 pi over 4. Sorry, 5, nope, that's wrong too. That's going to be 4 pi over 3. Yeah, absolutely. So 240 degrees is the same thing as 4 pi over 3 radians. So in order to use this arc length formula to find the S I'm looking for, I'm going to multiply the radius, which is 4. And again, it's 4 what? It's 4 inches times my radian measure, theta, which was 4 pi over 3. So when I do 4 times 4 pi over 3, that's going to be 16 pi over 3. And notice my units are in inches. Again, think about the problem that would occur if I multiplied this was degrees by inches. Then my answer would be in degree inches. Well, that doesn't even make sense because degree inches is not a unit that we can use. But when we write it in radians, radians are unitless. We don't have to include radians. So when I multiply inches by radians, my final answer is still in inches. That's a unit that makes sense to us. So the arc length here would be 16 pi over 3 inches. And if you put that in your calculator, if they wanted a decimal representation, that would be approximately 16.76 inches. Okay, so here's a problem that's similar. So I want you to pause your video, see if you can work it. Okay, so it gives me S equals R times theta. Again, is my formula to find the arc length. And then I want to set up what it tells me here. I've got a circle. The radius is 27. And I'm looking for the arc length whenever I'm rotating 160 degrees. So you're going to want to convert 160 degrees to radians. So that would be 16 over 18, which would be 8 over 9. So in radians, that's going to be 8 pi over 9 radians. So your arc length would be 27 for the radius times 8 pi over 9 for your theta. And when you multiply those out, you should get 24 pi inches, which if you make that into a decimal, that's approximately 75.4 inches. Okay, so it says here's our formula for both linear and angular speed. So the linear speed is going to be kind of familiar to you. When we find linear speed, that's the distance traveled divided by the time it takes to get there. So it says here, when I'm finding linear speed, even if I'm moving along a circle or along an arc, to find the speed in a straight line, I take the arc length and divide it by the time it took me to do it. If you think about traveling in a car, right, that gives you linear speed. You're taking distance divided by time. It's the same idea. This is the distance you travel along the arc of the circle and divide that by time. Miles per hour, feet per second, right, whatever it is you're working in. Now, here's the one that's a little bit different, that's more specific to trig. It says if theta is an angle, and again, that angle has to be in radians, and it corresponds to the arc length s, then the angular speed, that's how fast you are going in relation to the circle, right? Again, thinking back to that merry-go-round. Then the angular speed is given by the central angle, so how much did we go around, divided by the time it took to go there. Linear speeds measure how fast the particle moves, and angle speed measures how fast the angle changes. So, again, the deal here is, with your angular speed, think about that merry-go-round. If I was going from this position to this position along the merry-go-round, my linear speed, if I was out here on the outside, I'm traveling a greater distance because I'm on a farther track than if I was inside. If I was standing in the center of the merry-go-round and I move from there to there, I'm not traveling near as far. So your linear speed changes depending on where you're standing in relation to the circle. But the angular speed is constant. No matter where you're at in the merry-go-round, it's still traveling the same angular speed around. It's kind of confusing, and I'm probably not the best at explaining it. But like I said, hopefully you can kind of see the different kinds of speeds that we're measuring here. The second hand of a clock is 10.2 centimeters long as shown in figure 4.11. Find the linear speed of the tip of this second hand as it passes around the clock face. So because I am looking for linear speed, I'm going to use the linear speed formula, which is velocity equals s over t, where s is the arc length, the amount that it travels along the outside, and t is the time it takes to do that. So in this problem, I'm looking for linear speed. I'm looking for v. All right, so let's think about how far does it travel. So I need to find the s and the t. We're talking about as it goes around the clock, so let's think about it going around in 1 minute. So as it goes from there to there, what is the measurement of the arc? If you think about it, it's just a circle. Right? That circle has radius 10.2, and the circumference is found by multiplying the radius times 2 pi. Right? 2 pi r. So to find what's in red, I'm going to multiply 10.2 times 2 pi, which means the circumference here is 20.4 pi inches. Centimeters. So this is my arc length. This is my S. So I plug that in here. And then how much time does it take to travel? Well, it's going to either take 60 seconds or 1 minute, depending on which unit it would like for me to get as the answer. So it doesn't specify if it needs to be in seconds or in minutes. I'm just looking. I see that they gave their answer in seconds, so I'm going to give mine in seconds. But either one would be acceptable if they don't specify. So the velocity is equal to the arc length which is 20.4 pi, divided by the time, which is 60 seconds. And so I'd put that in my calculator, 20.4 pi centimeters divided by 60 seconds. That means it's going to travel 1.07 centimeters per second. Right? We have to make sure we keep those units, centimeters over seconds. And this is an approximation. This has been rounded because you're going to get something pretty ugly dealing with that pi. All right, so try this one. You can pause the video and then I'll work it. So it says here, if I have a clock, this time the second hand is only 8 centimeters long. Okay, but that is my radius. And it's the same setup. If we're finding the linear speed, V equals S over T. So if I'm wanting to go all the way around the circle, that's my S. That is the arc length. So to find how far that is, I'm going to do 2 pi times the radius, because all I'm really finding is the circumference. So that's going to be 16 pi. This is my S. And then same thing, my T is 60 seconds. So this time it's going to be 16 pi centimeters divided by 60 seconds. You would put that in your calculator. You could find the velocity was approximately 0.84 centimeters a second. So this time the speed's not quite as fast because, think about it, the distance here is not quite as long, just like we talked about with the merry-go-round. This time we're actually a little bit closer to the center because it's a little bit shorter. So the closer you get to the center, it's not near as fast on those merry-go-rounds. Okay, here's the last one. This one's going to be finding angular and linear speeds. So we're going to be using both formulas. So the linear speed formula is one we just got done working with. V equals S over T. Okay, with the angular speed, that formula is a little bit different. If you look back on the previous examples, it says angular speed is equal to theta, which is your central angle, divided by T. And the way we write angular speed is we write the Greek letter omega. Okay, so that is an omega. I know it kind of looks like a W, and I don't know how to draw it, but it is actually an omega. That's a little O in the center. All right, I don't know if your book actually uses that, but in old textbooks, they use that. In physics books, you're going to get used to that. So that's what I'm going to use. But again, this is just the angular velocity, or the angular speed, and this is the linear velocity, or the linear speed. All right, so we're going to start. I know that this one does linear second, but I'm actually going to do linear first because that's what we've already been doing. So let's do B part first. It tells me to find the linear speed of the tip of the blade. So we see that this speed is given by the distance covered, which is S. So how much am I covering here? Well, this problem's a little bit different because it tells me that it does 15 full revolutions in a minute. So the last example we were working was a clock. Well, a clock does 1 revolution every minute because, hello, it's a clock. That's the whole point of the second hand. So this one, let's figure out, again, this is just a circle here on this wind turbine. Let's figure out what's the distance covered in 1 revolution. So again, I'm finding the circumference. So the circumference is equal to 2 pi times the radius, which is 116 feet. So that's going to tell me the circumference is 232 pi feet. This is the distance covered in 1 revolution, 1 time around. Okay, but to find the linear speed, it does 15 of these revolutions every minute. So there's different ways you could plug that into the formula. You could either, let's just talk about them. You could either multiply this number by 15, and then that would tell you your S over 1 minute. Right? Because in 1 minute, it's going to do this full cycle 15 times. So if that makes sense to you, you can do it that way. If you do it that way, your number on top is going to be very large, but your T will be nice to work with. It's just going to be 1 minute. Another way that you could do it is you could say, well, if there's 15 revolutions in a minute, that means there is 1 revolution every 4 seconds, right? Because 4 times 15 is 60 seconds. So then you could say that this is my S, and you could divide it by 4 seconds. All right, that's another option that you have. I'm going to go with the first option. I'm going to take 232 pi, and I'm going to multiply that by 15, and that's how long it's going to take, or that's how far it's going to travel in 1 minute, because it does 15 of those full revolutions. So again, calculator, you have to do 232 pi times 15, and then divide by 1 minute. That should give you approximately 10,933 feet per minute. Okay, so that had one extra step from what we've been doing, but I thought it would be nice to work with linear speed first, because that's what we've been working with up to this point. Now the second one is find the angular speed. So the angular speed, the theta needs to be in radians. How many radians did this travel? Well, we know 1 full revolution is 2 pi radians. And it did 2 pi radians 15 times in a minute. So we could multiply 2 pi times 15, which would mean my theta is 30 pi over, and then the time it took to do that was 1 minute. So that would be 30 pi over 1 minute. So 30 pi a minute. And again, that's talking about radians. So it did 30 pi radians every minute. Okay, here's the one I want you to try to do on your own. You can pause the video and then come back and try to work it. Notice here, we're doing the same thing. We've got angular speed, and then we have linear speed. But this time, look, 2,400 revolutions a minute. So the last problem was only 15 revolutions in a minute. This is a saw blade, so it's going to have a lot more revolutions per minute. All right, if you worked it out, A part, which is the angular speed, you should have gotten 4,800 pi radians in a minute. And then B part, which is the linear speed, you should have gotten 60,319 inches per minute.